This video is going to be stochastic integration, but before I rush ahead and define that, let's just do a warm-up. I'm going to remind you of some things about ordinary integration that are relevant. So in ordinary integration theory, if you just have a function f, and this is just an ordinary real-valued function of a real variable, nothing random about it, then when we write the integral from a to b of f of x dx, what we usually have in mind for that is the so-called Riemann integral. It's the limit of sums that look like this. Where we've taken our interval from a to b and we've subdivided it in some way or other, like so, t0, t1 up to tn. We've made a partition of the interval, and the things we're summing in the big sum here are the width of each interval, or the elapsed time, if you're thinking of t as time, multiplied by the value of the function around there. Sum that up and you've got a sum which approximates the integral, and if you take the limit of that as the partition gets finer, you should get the integral itself. This once again is one of those integrals that is supposed to be taken, one of those limits that is supposed to be taken as the partition is refined. Right, so that's an ordinary integral, that's what that looks like. Also, suppose we have another function called g. You also sometimes see this. If it was the limit of this sum, where instead of the elapsed time t, ti minus ti minus 1, we take the increment of the function g. So instead of just elapsed time, it's elapsed something, the increment of the function g. That's sometimes written as integral f of x dgx. That's called a Stochastic integral, or a Lebesgue-Stochastic integral, and you've implicitly done something like that if you've ever done an integration by parts. That's going to be important in just a moment. Stochastic integration. Here it is, the real thing. So now we're going to have a random function or process xt, that'll be an Ito diffusion, and another one ht, which doesn't have to be an Ito diffusion, just any Cadillac random function will do. And they're both adapted to some filtration ft. So among the things that you know, time t is the values of both of these things. And now we're going to define the integral. Traditionally you do this just from 0 to t, so always over an interval that starts at 0 rather than a general interval a to b, although it could be any interval, but most books just have their interval always starting at 0. The integral of hs dxs, which we'll define to be like this. It's the limit of a sum like that. So it's like the Stochastic integral. The increment of x times the value of h. And again, it's the same old story. The interval in question, 0 to t, is subdivided into many parts, t0 to tn, and the limit is supposed to be taken as that partition is refined. Let's call that yt. That limit, because we're dealing with random functions now, the questions arise as to, in what sense does this limit exist? And I've already talked about this before, so I won't go through again the different senses in which a limit can be said to exist when there are random variables involved, except to say that the remarks I made earlier about the three different kinds of convergence that are possible all apply to this as well. So if you really want to know the nitty-gritty of how the limit works, you can go back to the earlier occasion when we discussed convergence. That was when we were constructing the isodiffusion in the first place, and all the remarks that I made there apply here too. Now, the reason I called this yt is because the next thing we can do is make t a variable. So we can now have yt thought of as a random function itself. It's a function of t. It's the sort of indefinite integral of h dx. So that makes it a random function too, and in fact it is an isodiffusion. And also adapted to the same filtration. How can we easily see that? Well, it's actually not too difficult to see loosely why that must be true. If you look at what the increment of the process y is, so that's the increment of the y process from t to t plus delta t, what will that be approximately? Well, because of the way that yt was defined, that'll be approximately ht times the increment of the process x. And we know sort of loosely what that is. The increment of the process x, let's just focus on that for starters. So if we didn't have this ht here, we'd just be looking at the increment of x, which we've seen before is, according to the definition of isodiffusion, is normally distributed with this mean and this variance, where ut and vt are the drift and speed of x. And the only change we've made multiplying by this ht here is to scale the thing. Remember, ht is, that process is adapted to the filtration ft, which means at time t this is known, which means if we're looking at distributions conditional on ft, which we are when we're talking isodiffusions, this is like a constant. So all we have to do is stick in the effect of multiplying by a constant. The mean gets multiplied by that constant, and the variance gets multiplied by that constant squared. So this is one way of making new isodiffusions out of old ones. If you've got an isodiffusion x and some other function h that you've dreamed up, you can do a stochastic integral like this and get a new process yt, which is also an isodiffusion. Because this is so common, we have another way of writing it. This is the standard sort of notation to describe what we're doing here. dyt equals ht dxt. When we write this, we mean this. Yt is the stochastic integral of h dx, defined as a limit of sums in this way. And that's something you see a lot. It's a notation we'll be using a lot too from now on. Time for an example. So w here is a Brownian motion, and we are going to work out the integral of w dw. And it's going to turn out to be this, half wt squared minus t, which should surprise you. If w were just an ordinary function, not a random one, then the integral of w dw would be half w squared. Somehow, mysteriously, the fact that it's a random function changes the answer and means you get this extra term. I'm going to work through actually working out what this integral is on the basis of the definition as a limit of sums, because I think that's one way of looking at where the extra term comes from. So here we go. We've got the interval 0 to t, and we're going to divide it up in a partition like this, t0 to tn. To make it easy on ourselves, we won't just take any horrible partition, we'll take a regular one, so t sub k will be k over n times t, for k from 0 to n, so each little subinterval in the partition will be the same length, they'll all be of length t over n. And then the sum we've got to write down is, according to the definition, it's the sum from k equal 1 to n of w, let's write it like this, tk minus 1 times w tk minus w tk minus 1. That's the approximating sum that we've got to take the limit of. And now what is this in terms of its distributions? Well, we know the increment of a Brownian motion is normally distributed, and now this thing is the actual value of a Brownian motion at a point in time, which is also normally distributed. But these two things are not independent, so when we multiply them together, what do we get? It's all looking a bit of a mess. A good tip for these situations is to try to get things written in terms of independent random variables. That often makes it a lot clearer to see what's going on. And we can actually do that here like this by splitting up this value of the Brownian motion as the sum of all its increments up to that point. So we'll make it sum like that of, now this guy is okay, we'll just keep that as is. And now this thing, that's the sum for j equals up to k minus 1 of the increment. And so the sum of all the increments of the Brownian motion up to time tk minus 1, which is what we want there. Okay, and now we've got it all written in terms of the increments. To make it a bit nicer when written down, I'm going to introduce a shorter way of writing this. I'll write zk for the increment of the Brownian motion, and while I'm at it I'll normalize it by dividing by its standard deviation. It's already got mean 0, so there's no point subtracting the mean, but I will divide by the standard deviation so as to make it have a standard normal distribution. So these zk's, so z1 up to zn we've got now, not only all standard normal distributed, they're independent standard normal distributed. Remember, it's a key property of Brownian motion that its increments over non-overlapping time intervals are independent. So, all right, what have we got now? Approximating sum that we are working on is, it's this. K equals 1 to n, and from j is 1 to k minus 1 of, I can write this zk, and the other increment is zj, and to take account of the normalization, I should put in an extra t over n. Right, each of these things is already divided by the square root of t over n, so now I have to multiply by t over n. Okay, that makes it a bit clearer what we're looking at. We're looking at one of these double sums of normally distributed things, a bit like a U statistic if you've ever come across those. Now what have we got in terms of a... Always have to draw a little diagram in these situations. Double sum, k is going from 1 to n like that, and j is going from 1 to k minus 1. So the bits of the jk plane that are being summed over are in this triangle. And the reason I'm doing that is that you can write this now as a double sum like this. How about I sum over all j's and k's of zj, zk? So that would be over the whole of this square here, except that I'll leave out the terms on the diagonal where j equals k because we weren't supposed to include those, and I've also included all the ones in this other part of the triangle where j is greater than k. We were only supposed to include the ones where j is less than k, but now we're including the ones where j is greater than k as well. But that's all right because they are just symmetric. This zj, zk is the same if we interchange j and k, so all we've got to do to allow for that is put in an extra factor of a half. In effect, we've added a whole lot of new terms, but the new terms are the same as the old terms, so if we just include them anyway and divide by 2 at the end, we'll get the same answer. And the reason we're doing that is so that we can write it like this. If we sum over all j's and k's except the ones where j and k are equal, that's almost the same as just summing them all just themselves, single sum, and squaring the answer. If you think about what happens when you take this whole sum z1 to zn and square it, expand out that squaring, you'll end up with exactly this, except that you will also have some diagonal terms which we've not got, so we'll have to subtract them away. That's a 1. So we can write it like that now. Now, I was aiming for this because what's the sum of the zk? Right, if we sum up all the zk's, well, the zk's, remember, were just increments of the Brownian motion, normalized a bit. So if we add them all up, we're getting the total increment of the Brownian motion over the whole interval from 0 to t, normalized. So that will be the whole increment divided by the square root of t over n. So that's my whole wt minus w0, but w0 is 0, so just wt divided by the square root of t over n, and we've got that squared. And then this is being multiplied by t over 2n, but the t and the n is going to cancel out there in a minute. And for the other term, like that. So this first term looks very nice now. That's just a half wt squared with the t's and the n's cancelling. And what about this part? Well, here we've got the sum of n independent random variables. So we're back in the sample mean situation. You're adding up independent random variables. And we've even got an n down here, so if we include that, it's exactly a sample mean. So we've got t over 2 times sample mean of a sample that is drawn from what distribution? It's drawn from the distribution of a standard normal squared. We don't have to know anything about that distribution except for its mean. That's going to converge to the expectation of a standard normal squared, which, as we all know, is 1. So finally then we get the answer half wt squared minus t. Notice how that extra term that we weren't quite expecting, the t here, that came out of these terms on the diagonal where j was equal to k. And I'll talk about that more in a minute. Getting back now to the way stochastic integrals are defined as a limit of sums like this, you'll notice at this point a key detail is that when we write this sum, the integrand, h, is evaluated at the left endpoint of each subinterval. So a subinterval from ti minus 1 to ti, you evaluate the function h, the integrand, at the left endpoint, ti minus 1. Now that's a detail that for ordinary integration really doesn't matter. You can define an ordinary integral like this as a limit of sums, and when you write that limit of sums you can write it this way. Or if you prefer, you could evaluate the integrand at the right endpoint of each subinterval. You could just write ti, or maybe the midpoint of the subinterval, or some other point in between. It really doesn't matter when you're just doing ordinary integration, the sum will converge to the integral regardless. But when random functions are involved, it is actually crucially important that you take the left endpoint of the interval. So in this definition, we're noting that the left endpoint is used. In other words, we are not doing this. We are not taking the sum I from 1 to n hti times the increment of x. Why does that matter so much? Well, what difference would it make? So what would be the difference between that and that, between the two sums? Well, let's just subtract them and write down what the difference is. It's the sum from I equals 1 to n. They both contain the increment of x just the same, but we have like so. Both contain the increment of x, but one of them has the h at ti and one of them has the h at ti minus 1, so if we take the difference it would be this. Which might look familiar because this is the sum that we described a time or two ago as being, in the limit, the quadratic covariation of the two functions, h and x. So the difference between having a definition with the left endpoint being used and having the definition and use the right endpoint, the difference it will make to the final answer, the integral, is equal to the quadratic covariation of the two functions. So if you've got two stochastic processes whose quadratic covariation happens to be 0, then it doesn't actually matter where you take the evaluation point for the integrand. Could be the left endpoint, could be the right. But if the quadratic covariation is not 0, as it sometimes isn't 0, then it does matter. We've actually just seen an example of that. In the example we were doing just now, the integral of ww, that is a case where the quadratic covariation isn't 0 because we're talking about the quadratic covariation of w with itself, which would be its quadratic variation. And we've already seen that the quadratic variation of Brownian motion over an interval 0 to t is t. telling us that if we defined this integral the other way, right endpoint instead of left, it would change the answer by t. And in fact, if you work that one out with the other definition, you can work it all through exactly the same way, and you see that what happens is that the answer you get is the same as this, except that this minus is a plus. So instead of minus a half t, you get plus a half t, the difference being t, which is the quadratic variation of Brownian motion. There are actually, the definition of stochastic integral that I've given here with the left endpoint is the standard, particularly for applications in finance, and we'll see eventually why that is. But one could imagine using the right endpoint instead, and that gives rise to a completely different theory of integration in which the values of all the integrals are different, or at least many integrals have different values. There's even a version where you evaluate at the midpoint of each subinterval, and that's yet another different definition which gives some integrals yet other different values. So these are all kind of separate, independent theories of stochastic integration. But the one we're going with is this one, left endpoint. Getting back to the quadratic covariation and being zero, we've seen some situations where the quadratic covariation of two stochastic processes is zero. So one situation where it's zero is if either h or x is a finite variation process. That makes the quadratic covariation zero. The other one is if h and x are independent. That makes the quadratic covariation zero. But in general, neither of these two things is the case. In fact, as we've just seen in that example, h and x might be the same stochastic process, in which case the quadratic covariation is not likely to be zero. And in that case, it really does matter which theory of stochastic integration you're using, and you have to remember the left endpoint is the one we're sticking with.